Okay, so visualize this. I have 2 nickels on the green spinny thing. We're going to go around like this. They're going to make 30 revolutions per minute. Okay? Start with this. Is 30 revolutions per minute period or frequency?
Frequency.
Frequency. Yep.
Frequency.
Because it's an event per unit of time.
Yeah.
Right? Frequency. Cool with that. Which one takes longer to go around? The outside quarter, or the outside nickel, or the inside nickel?
Outside.
Amount of time.
Same amount of time.
Same amount of time. They're both making 30 revolutions per minute.
I said same.
I'm tired of that.
It's the same. Now, what are the forces acting on each nickel? So,
Gravity, force normal.
here's the side view.
And
Here's the
force
nickel.
centripetal.
What do you have?
Force gravity. Force.
Gravity, normal,
Friction. Wait, no.
and
Force-
friction's creating what?
The inward
Force
force.
centripetal.
The centripetal force. Which direction does any centripetal force act?
Inward.
At a
90 degrees.
to the velocity vector.
Listen, why would they fall off if you went too fast?
Because just like a string would break if I try and swing a bowling ball around over my head,
I think we should try it.
I don't. Okay,
Let's take it down.
now, here's the whole key to this. So let's talk about a couple of things. Are both quarters undergoing centripetal acceleration?
Maybe.
Yes,
Yeah.
Yes, why?
because they're
Because they're both
both getting.
We're both moving in a circle, right? So part of the challenge that you're going to face tomorrow, or excuse me, on Thursday for this test, are the equations that are not on your sheet. So basically you have centripetal acceleration equals v squared over r. That's what you have, okay? But you need to be able to substitute in, oh, that v squared, I can write that as 2 pi r over t squared over r, which becomes 4 pi squared r squared over t squared over r, which simplifies down to 4 pi squared r over t squared. Now, if you go what Vanessa had talked about earlier, since period and frequency are inverses of each other, this can also be written as 4 pi squared
F.
rf squared. Okay? All right? So be fluent in being able to drive these equations. So which nickel, based upon those equations, undergoes the greater centripetal acceleration?
I think the outside one.
The outside one or the inside one?
I think
Outside.
Outside one, because frequency is going to be the same for both of them.
Yeah.
Yeah.
So as the radius gets bigger, what happens to the centripetal acceleration?
Bigger.
It increases. Cool. You can also look at it in terms of this. Since both nickels take the same amount of time, t is the same, radius gets bigger, centripetal acceleration gets bigger. Cool. Now, you also know that mu equals force friction over force normal, right? So, this harkens back to something that we talked about just a minute ago. What creates the centripetal force to make that thing go around? It's either a string, gravity pulling inward, or friction.
Friction.
Let's go with friction. So I can substitute centripetal force in for force friction, because that's what that's creating, right?
Correct.
And you go, oh, that's mass times centripetal acceleration, that's mg. So you can look at mu as being a ratio of centripetal acceleration to your gravitational acceleration, okay? But there's a limit to what friction can do. So when you look at this, mu is going to be the same for both of them based upon the coefficient of friction because it's the same surface. So what that means is the one that's further to the outside is going to require a greater amount of centripetal acceleration. So that means that that one is going to exceed that frictional force first. So as this goes around, and I sped it up, that outside one flew off first because it exceeded the frictional force before the inside one did. Okay? Now, if I put it on this rough surface and then make it go around, I can go pretty fast before that flies off. So why could I go much faster when it was on the skids?
It had
Friction
more
was way bigger.
Friction was a lot bigger,
Yeah.
okay? Since that friction was a lot bigger, I could go a lot faster before I exceeded the limit of that, okay? Cool with that. Now, here's gonna be, let me go get my rubber stopper. I promise you, there's gonna be ones where you deal with vertical motion like this, okay? So, quick refresher. As this goes around in a circle, when is the string most likely to break?
It's on the bottom.
Top or bottom?
Bottom.
Bottom, why?
Gravity.
Yeah, gravity and-
the centripetal
yeah.
force at the same time.
Is gravity stronger at the bottom?
Yes.
Yes.
Well,
No.
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 No, gravity is the same.
The net force is stronger at the bottom.
There's a bigger
Why?
net force.
Because gravity adds to the force centripetal.
Yeah, so
Or
I have to provide two forces at the bottom. I have to provide the force to keep it moving in a circle, and I have to provide an upward force to balance out the force of gravity.
Yes.
Gavin?
How does force centripetal add to the gravity if it's going up into the circle?
Because the tension has to balance out, you're looking at the total force that's gonna be on the tension of the string. So right now, how much tension is in the string?
How much ever that weighs.
Yeah, which is just gonna be mg. So the tension right now is equal to mg.
Yeah.
Correct.
Yeah.
So now, if I can make this thing move in a circle with no gravity, if I could shut off gravity, how much tension would there be in the string? Enough to create what? The centripetal force, because I gotta make it move in a circle, right? So if I make it move in a circle and there's no gravity,
It's the same throughout.
yeah, it's the same throughout, it's not gonna change. Because it's just gonna be the same amount of centripetal force. So when I combine the two of them together, the tension acting up has to do two things. It has to make it move in a circle, and it has to keep it from falling.
I think I get it.
Okay, there's not a lot to get, okay? Now, when you're at the top, and again, these are equations that are not on your equation sheet.
Shucks.
So, but again, just think this through. Oh, at the bottom it's gonna feel heavy.
Yeah.
So your total force, your net force, however you want to think of it, is Fc plus Fg. And don't get weird and make that negative 9.8, okay? Just add the two numbers together. Do not get weird. Do not make this complicated. Just get the numbers, add them together,
Okay.
okay? Now, at the top, your total force is going to be force centripetal
Minus.
minus Fg. And again, don't get weird and, oh, I'm going to subtract a negative 9 point. No, it's still balancing out. The total force is going to be the difference between the two. So, we work problems like this. I promise you there's going to be a question like this. Up at the top, you want to feel a specific percentage of what you normally feel. So I can say, okay, here's this roller coaster. And I'm going to say, you want to feel 1/8 of your normal weight. Okay? So what you feel is that total force. Okay? This is what you're going to feel. 1/8 of what you normally feel.
Indeed.
The only thing I can do is change the fraction. 5/16, pi, whatever. That's it. Only thing I can do is change this number. That's the only thing that I can do. And that's going to equal force centripetal minus Fg. And it's always going to be at the top. Okay? It's always going to be at the top. So, I'm going to add this over. I'm going to take 1/8 plus Fg and get what?
9/8.
9/8. So 9/8 FG, which I'm gonna put as mg, is gonna equal mv squared over r.
Yes.
What's gonna happen to the mass?
Cancel.
So I get v equals the square root of
I'm so sorry.
9/8 GER. Okay?
Yes.
Oh, the M's canceled.
So literally, in this process, what's the only thing that I can change?
A fraction.
Fraction.
That fraction. 1/2, 3/4,
We're
7/8.
given V equals GER, right?
Huh?
We're given V equals GER, right, on the test?
You're given what?
You remember V equals GER, did we get that on the
No.
test? Oh, no bueno.
No bueno.
That's not that hard to remember.
Well, it's just, if you're in a state of weightlessness, you want to feel 0 FGs, right?
Yeah.
Mm-hmm.
So that just means your centripetal force equals your gravitational force.
Yo, that's tough.
And then, oh, that's mv squared over r equals mg. The minimum velocity is the square root of GER, which is the same velocity that you need to be in orbit very near the surface of the Earth.
Okay.
So if you wanted to figure out how fast, here, let's do this. Oh, what's the velocity that we need to be in orbit around the Earth? So somebody take 9.8 meters per second squared times the radius of the Earth, 6.3713, times 10 to the 6th meters. So multiply those two numbers and take the square root of that.
I can't.
What do you get?
Is it like 800?
1, 2, 3, 4, 5, 6.
I literally can't.
7.90 times 10 to the 8th.
So basically 8,000.
Oh, 8,000.
That's a lot.
Now, quick review.
Yeah.
If something's in a near-Earth orbit, what do you know by the order of magnitude of the orbital period? In seconds, what's that going to be? 10 to the what? Third.
Oh, yeah.
Velocity is also going to be
The third.
10 to the third. Unless you're way out in like a geosynchronous orbit, here's your magic numbers. And the same thing is going to be true of the moon. Okay? Orbital velocities, orbital periods around the moon are going to be 10 to the third. Okay? If you ever get 10 to the 6th, you probably forgot to take the square root of something.
Probably.
Okay? Just saying. That's probably what happened. Okay. So make sure that you can do that. Yes, there's problems like this on the review. Okay? Let me see. There's the problem with the tetherball. Make sure you can do that. Make sure that you can work ratios using Kepler's, or basically derive Kepler's laws. Okay? Figure out what's going to remain constant and what's going to change. So there's two kind of ideas that tend to get muddled in this. So one is that equation for little g equaling big G, mass of the Earth over r squared. Okay? What this one gives you is a couple of things. It gives you the acceleration of a dropped object. Okay? So if you're the science officer on the spaceship Enterprise and you land on a planet and you happen to know the radius, because that's relatively easy to see, you can look at it from a distance and go, okay, here's an idea of what the radius is. And if you can figure out what little g is on that planet, you drop something, oh, what's the acceleration? You can figure out the mass of that planet, okay? So this equation gives you the mass of the planet, okay? Not the mass of the star that it's orbiting. This is the mass of the planet. Now, when you look at 4 pi squared r cubed equals big G mass of the planet times t squared, this gives you the mass of what you're orbiting, okay? So this could be a star, it could be the Earth, it could be a moon, okay? So this only works when you're talking about something that you're dropping. Here's the value of little g. This is something that's in orbit around it, okay? But here's where these two ideas cross. is that, let's say, for example, I give you information about a satellite, okay? So what you have to be careful of is that, do I tell you, is that the distance above the planet, or is that the orbital radius? If I just tell you that's the orbital radius, you don't have to do anything with it, just leave it, that's it, okay? That's it, you're done. But if I tell you that it's a certain distance above the Earth or something like that, or above the moon, then you need to add in the radius of the moon, the Earth, whatever that is, okay? But here's where these two ideas cross. At any point, once it's actually in orbit, little g is going to equal your centripetal acceleration, okay? So again, there's a whole bunch of different ways you can look at centripetal acceleration. You could use v squared over r. You could use 4 pi squared r over t squared. And all of that's going to equal little g. So here's the idea, is that, and I promise you, you're going to have a problem like this. I'm going to give you information about a satellite. I'm going to say, hey, what's the centripetal acceleration? Or I might say, what's the value of little g at that altitude? Whether you find the centripetal acceleration or you find the value of little g, it's the same thing, okay? Because what's creating the centripetal force is gravity. So that's what allows you to set the centripetal acceleration equal to little g, okay? Be able to work problems where I say, all right, for example, I might say, here's your equation for little g equals big G mass of the Earth over r squared, okay? And I might say, all right, I want g to increase by 3. Assuming that the mass of the Earth remains constant, what would be the new radius? So in other words, here's the story. We want little g to increase by 3 times. We want it to be like 27.9. What are we going to do to the radius to make g go up by a factor of 3? So let's start with this idea. Just the idea. Is the radius going to get bigger or is the radius going to get smaller?
Smaller.
Smaller. I need to divide by a smaller number. Okay? Now, if it was just r, if it was just r, not r squared, it was just r, what would I do to the radius to make g go up by a factor of 3?
Divide r by 3.
I divide r by 3. I shrink the radius by 3. Okay? It's squared. So what am I going to do?
Square root 3 divided by that number.
So I decrease the radius by the square root of 3. Because then when I square that, that becomes r squared over 3. Okay? So be able to think through problems like that. And I've told you this before, and I'll tell you this again. It is just as vital that you understand what is in the equations and also what is not in the equations. So like that problem we worked at the beginning, and it told you the mass of the satellite doubled. That was a red herring. Why?
Because the mass canceled out.
Mass doesn't matter, okay? Great, mass of the satellite doubled, cool, who cares? Now, do you care if you're designing the rocket to get it into orbit? Yeah, you care about that a lot. But once it's in orbit, I don't care what the mass is, can't plug it into the equation if I tried, okay? Here's the best advice I can give you. Be fluid with the equations. Know when to use each one. Know how, like for that Swiss Army knife, 4 pi squared r cubed equals big G mt squared. Be able to easily solve for each one. Pay attention to the units. If you're involving anything, if you see any calculation that involves big G, you have to be in the MKS system, okay? You have to be in the MKS system. Now, if it's just ratios, doesn't matter. But if you're doing a straight calculation with big G, you have to be in the MKS system. Now, before I forget, I meant to say this earlier. There was this question on number 39 of the book. And if there, where it's got, problem 39. What's the gravitational force of the sun and the earth? What's the gravitational force of the moon and the earth? The moon's force is what percentage of the sun's? I know the answers in the back of the book. I better see, those are some very complex calculations, okay? I want to see those calculations of force and then the percentage, that percentage calculation, okay? So if all you do, again, on 39, is if you just go to the back of the book and you write down those numbers, don't even bother, okay? Such bad things are going to happen. Such bad things are going to happen.
That one's just the Swiss Army knife, right?
Yeah. Oh, no, 39, no. No. That's F equals big G. You're trying to find the
Yeah.
gravitational force
Oh, yeah.
of the sun on the earth
Yeah.
So F equals G
So
M1
just
times
G
M2 over
and-
D.
over D squared, yeah, or R squared, depending on how you want to view it, okay? Anyway, there's all that. On that question on the sheet that I gave you, on question number 13, because if 13A is wrong, it's all gonna go wrong. So your answer to 13A, you want to calculate the gravitational force between an electron and a proton, separated by a very, 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 very small distance. So your answer to 13A should be something times 10 to the negative 47th.
13 should be what?
13A should be something times 10 to the negative 47th.
What the freak? Oh wait, it's electrons.
And protons, and you're trying to find the gravitational force between them,
Okay.
okay?
Oh, they really don't like each other.
No, they do, because they're oppositely charged, but that isn't, charge has nothing to do with your calculation on 13A. That's just based upon mass and distance. They're just really, 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 really little. Okay, so, I'm gonna give you those two parts to the review. One is just the centripetal motion part, and the other one is the gravity part. There's going to be this question on number 3 with the centripetal motion part, and it talks about something going, a roller coaster going down an incline. I will not make you do that part of it, okay? If you just want to jump to and use the velocity to figure out the rest of it, you can. I just kind of put that, if you want a refresher, on inclined planes, okay? If you just want to straight to the centripetal motion part, just get the velocity from the answer key. So,
Will there be one like that on the test where it's like you have to know the incline?
Huh?
Will there be one like that on the test where you have to know how to do that first part?
no, that's what I said. I won't make you do the first part. I will just go straight to giving you the velocity, okay? But on this one, it says, E, what's the velocity at the top where you experience 1/6 your normal force weight? If you don't do anything else, make sure you can do 3E, because there's that fractional problem. When you get to, on this one, question number 6, you're spinning in a barrel. You guys don't worry about number 6, okay? Because the AP exam never gives you one where you're spinning around in a circle and you're stuck up against the side of the wall. So don't worry about number 6, okay? It's not going to be on the test. Don't worry about it. Don't flip down and go, oh my God, we never had a problem like this. Okay, don't worry about this one, number 6, okay? Worry about everything else, especially number 5. When you get to the satellite problems, okay? And when you get into these, again, be fluid in these equations. If there's one set where, hey, I'm not even going to look at the answer key until I get done, do that with the satellite problems, okay? And if push comes to shove, if you are hurting for time, if you do nothing else, you do, which one is that? Number 16, that last problem. If you don't do anything else, will you work number 16 on the satellite problems, okay? Because I promise you, there's gonna be one like that, okay? All right, I'm done.